Hello, this is Jianer Chen, professor in computer science and engineering at Texas A&M University. The title of my presentation today is The Arts of Satisfiability, Algorithms, and Complexity. So let's start with the definition of the problem. So what is the satisfiability problem? SAT, SAT. Okay, so the problem is stated as this. So given a Boolean formula in CNF form, i.e. this is a conjunctive normal form, we need to decide if we can assign the variables in the formula to make the formula equal to 1. Here we use 1 for Boolean value true and a 0 for Boolean value false. Okay, so for example, this is an instance of the SAT problem. Okay, let's give some terminologies here. So a Boolean formula in CNF formula, a CNF formula is given like this. So you have this parentheses here, which are called clauses. Okay, the clauses are connected by the AND operation, and as a Boolean operation. Okay, and within each clause you can see variables or negation of variables, which are called literals. So the literals in each clause are connected by the OR operation. Therefore, in order to make the formula equal to 1, you have to make all clauses equal to 1 because clauses are connected by the AND operation. On the other hand, in order to make a single clause equal to 1, you have to have at least one literal in the clause to have a value 1 because literals in each clause are connected by the OR operation. Okay. In particular, for this formula, if you make assignment like this, okay, then you can easily see that this assignment make the formula equal to 1. I marked those literals with red to indicate that those are the literals that have value 1 under this assignment. So you can see that every clause has at least one red literal. Okay, so that means this formula is equal to 1. So in particular, for the satisfiability problem, if this formula is a given, if the is the given instance, then our answer should be to this instance should be 1. Okay, should be yes. Okay. So you might ask, are there any kind of formulas that cannot be satisfied? Here's an example for this. So there's a literal, with two variables, x1, x2. It's easy to verify that no matter how you assign the variables, at least one of the clauses has a value of 0, i.e. there's no assignment to the variables that can make this formula true, this formula equal to 1. Therefore, the satisfiability problem with this instance, okay, should give an answer no. Okay. So then why this satisfiability problem important? Okay, well, number one, that has a lot of applications. Okay, here I quote a paragraph from the Handbook of Satisfiability, which is published about 15 years ago. I'm sorry, about 10 years ago. So from this paragraph, you can see that satisfiability is not just a problem in any single area. Actually, that has applications in many areas. In fact, this problem has been a basic model, okay, in problem solving in many areas. Okay, so here's we know that artificial intelligence currently is a very hot topic. Okay, here's a book recently published, AI book. If you look at the table of contents of this book, that has an entire chapter, okay, talking about satisfiability problem and its its algorithms. So that shows that the problem is of general interest, okay, and that has many applications. Well, the problem is also the first NP-complete problem. So what does that mean? Okay, this actually says that this is a representative of a very famous class of problems, okay, which is called NP-complete problems, the class of NP-complete problems. So this class of problems have the following interesting, you know, um, properties. Number one, they are extremely important and useful in applications. Number two, okay, so far there's no non-efficient algorithms that can solve any single problem in this class. Okay, we say there's no known algorithm. Actually, has been after many exhaustive efforts from thousands of scientists, including those smartest computer scientists, mathematicians, and engineers. Okay, so the class, I mean, so that somehow shows that the problems here are important in practice, but are very difficult or challenging. Okay, for algorithmic development. Well, so because of that, somehow it's safe to say that a SAT problem is the most important problem in computer science. Well, there are many important problems in computer science. Okay, when we say a problem is important, well, that has to have satisfied certain conditions, right? Number one, that has to be very useful in practical computing. Number two, that has to be interesting, okay, and or say with depth, okay. For example, sorting is also a very important problem that has a lot of applications, okay. And but we all know that sorting problems can be solved in time n log n time, right? And we also know that actually, that's the best that we can do. So for sorting problems, even that's very interesting and very useful, but we do understand that pretty well. Okay. On the other hand, for satisfiability problem, okay, number one, that has probably a equally, have a equal size of applications as sorting. Okay. On the other hand, for its complexity and algorithms, we know very little about that. Okay, so far we still don't know what is the best way to solve it. Okay, so that makes the problem very interesting. So that actually has become a central problem in research in algorithms and complexity theory. Okay. Finally, we also want to mention that this problem is closely related to Hilbert's 10th problem. So this is among the, a group of deepest mathematics, problems. So that also shows the depth of the set problem. So we are going to concentrate on uh, the algorithmic and the complexity theoretical issues of this particular problem. Okay, so now let's start with the problem. Okay, so for satisfiability, we're studying the algorithms of the problem. So the problem is given like this, given a CNF formula, and we want to decide if there's assignment to the variables in the formula that make the formula equal to 1. Okay. Um, well, in order to measure the efficiency of algorithms for set, we have a number of parameters. Okay. The commonly used parameters n, which is the number of variables, m, which is the number of clauses, and also l. L is the number of the length of the input. So that means that once you give a CNF formula, okay, so if you just look the length of this and and measure the complexity of accuracy in terms of the length, okay, and for this parameters, so for the number of clauses, there's a 1.234 to the m algorithm. Okay, the algorithm was developed about 15 years ago. There's also a 1.066 to the L algorithm, which was developed by my former PhD student, Liu, and myself. This is about 10 years ago. Okay, but really, the most important parameter, okay, in algorithm development for satisfiability is n, i.e., the number of variables. So, in the following discussion, we'll concentrate on this parameter n. Okay. Therefore, here's an algorithm, fairly simple algorithm for set. So the algorithm does like this. For a given formula, you just try all possible assignments, okay, to the variables. Okay, so remember that each variable can have a value 0 or 1. That's the only two possible values a variable can have. Okay, you just try all the assignments to each variable. And for each assignment to the variables, you evaluate the formula and see if that, the assignment make the formula equal to 1. Well, of course, if any of those assignments, make the formula equal to 1, then of course the answer to the instance should be yes. On the other hand, if all assignments do not make the formula have a value 1, then of course the answer to the instance should be no. Okay. So this is very simple, right? But what is the complexity of this algorithm? So record that each variable can have two possible values. And suppose you have n variables, so in total, there are 2 to the n assignments to the variables. For each assignment, we also need to spend a little bit more time to evaluate the formula under that assignment to see if the formula equal to 1. So for fixed assignment, it takes really polynomial time, right? This is not very difficult. So let's assume that for a given assignment, you can evaluate if the formula has a value 1 in time n times m. Okay, so you should be able to do that. Then the above algorithm gives a complexity 2 to the n times m. Okay, for which we write a big O star of 2 to the n. Here that means because 2 to the n is much larger than n and m, and we are most interested in the factor that dominates the complexity. So whenever we write a big O star, that means we ignore a polynomial factor in the complexity and only concentrate on the exponential term, exponential factor in the complexity. Okay. Well, this is a fairly simple algorithm, right? It's natural to ask, can we do better than this? The answers are surprising, actually a bit surprising. In fact, there's no better algorithm than this simple algorithm. Well, that has been a fairly well-known open problem for many years. Okay, can we have an algorithm whose complexity is c to the n for set, where c is a constant strictly less than 2? For example, can we have an algorithm whose complexity is 1.99 to the n for set? Okay. Well, in the past 20 years, there's no progress on this. Okay. In fact, more recently, people have proposed a conjecture. This is called a strong exponential time hypothesis, SETH. Okay. The conjecture says that there's no such algorithm. Okay. Therefore, what do we do? Okay, so we have a fairly simple algorithm, and the conjecture says that we may not be able to do better than that. Okay, well, we still want to do something with this, right, for its importance. So we consider a variation, a restricted version of a set, which is called a 3 set. So the problem is basically the same. Okay, the instances are still CNF formulas. However, now we require that the clauses in the formulas, okay, have the following condition such that each clause contains at most 3 literals. So that's the reason called this 3 set. Again, we need to decide if the formula is satisfiable. Okay. So for example, this is an example. You can check that for each clause that has either 3 or 2. That could be also 1. Okay, literals. Okay. And why we study this problem? One is 3 set by itself is still NP-complete. Okay, i.e. it's still difficult. Number 2, actually the general set problem can be reduced to 3 set problem. That means that if you can solve 3 set problem efficiently, then you can also solve a general set problem efficiently. Okay. So you might ask why 3 set? Why don't we work on 2 set? But in fact, 2 set would be too easy. Okay. It is known that a 2 set can be solved in linear time. So that's a reason 3 set is probably the simplest but still difficult enough problem for us to look into. So here's an algorithm for 3 set. Let's see how we do this one. So basically the algorithm is like this. Okay. First you look at the clauses. If there's no 3 clauses, then the problem is a 2 set problem that can be solved, okay, in linear time. Therefore, we assume the instance still has some 3 clauses, i.e. the clauses that contain exactly 3 literals. Okay. So what we do is that we pick any 3 clause. Okay. And for this 3 clause, okay, let's consider this. So this is the clauses we pick. Okay. Then we try the following. So the 3 clause contains the 3 literals, L1, L2, L3. So recall that the L1, L2, L3 are either variables or negation of variables. Okay. So this is what we do. First, we assign the first literal equal to 1. Okay, so that you get 1 variable with a value. Then you recursively work on the resulting formula. Okay. Or you do that by assigning the first literal equal to 0, but the second literal equal to 1. So that would make 2 variables in the formula with values. Okay. Then you recursively solve the resulting formula. Or the third case is that what you can do is that you can actually assign all 3 literals in the clause to have values like this. Okay. And then this would give 3 variables values, and then you recursively solve the resulting formula. Okay. It's not difficult to see that if the formula is satisfiable, okay, then one of those 3 cases must be the case. Okay. Therefore, this is an algorithm solving the 3 set problem. So what is the complexity of this? So let's assume that the complexity of this algorithm is T of n, okay, on n variables. Then the complexity of this algorithm is given by the following, okay, recurrence relation. So you can see this. So suppose the input instance has n variables, then in case 1 here, okay, you eliminate 1 variable. Okay, in case 2, you eliminate 2, and in case 3, you eliminate 3. So that really says, in order to solve this formula with n variables, you have to recursively solve 3 formulas in which the number of variables are n minus 1, n minus 2, and n minus 3, respectively. Okay. Well, but this is still a little bit complicated, but it's you can show that if your complexity satisfy this recurrence relation, the any complexity of the algorithm is equal to 1.84 to the n. Well, look, this is better than 2 to the n. Okay, so this is an algorithm that solves the three-step problem. Well, there are a lot of more different approaches that have been proposed in solving the three-step problem. Here, in particular, we want to mention one which is called Schoening's algorithm, okay, which was developed about 20 years ago by Schoening. Okay, so here's basically the algorithm. We are not going to get into the details about this algorithm. Okay, instead, we conclude that if you use this algorithm to solve the three-step problem, then the complexity of this algorithm is 4 over 3 to the n. So basically, this is 1.333 to the n. Okay, and this algorithm was actually at that point it was really that was very impressive. Okay, so once people once Schoening proposed this idea, then a lot of following up work, okay, on three-step algorithms. Okay, so if you show that, if you see this sequence of the improving results here, so the complexity started from Schoening, which is 1.334 to the n, then that is further reduced to 1.3224 and a 1.323, 1.322, and a 1.321, and all this. And actually, all this are very good results. I regard it as very good results. Okay. Therefore, well, currently, okay, the status is the best algorithm for solving the reset has a complexity 1.308 to the n, okay, which was developed about 10 years ago. Okay, so you might consider, well, if you can do this with 1.308, can you further reduce that, say to 1.305, and all the way go? Probably you can go all the way. Eventually, you might be able to get something, okay, which is something like, okay, you get something like 1.001. Either can make the base of the exponent here to be arbitrarily close to 1. Okay. So now this becomes another open problem here. So for three-step problem, can you have algorithms whose complexity is something like a 1 plus epsilon, 1 plus delta to the n, where delta, well, could be not 0, right? But can that be arbitrarily close to 0? Okay. Well, the answer to this open problem is probably not. Okay. There's also a recent conjecture that is called exponential time hypothesis, ETH. This says that there's no way, okay, you can have algorithms over three set whose complexity is 1 plus delta to the n for arbitrarily small delta here. Okay. Okay, that is basically the current status for satisfiability problem in terms for for exact algorithms, i.e., if you want to solve the problem, exactly. Okay, and the next we're going to discuss a variation of the satisfiability problem, which is called a Maxset. So the formula is given like this. The instances of the problem are the same as satisfiability problem. You have seen that formula, but you want to find assignment. But this time, instead of deciding if there's assignment that make the formula have value 1, now we want to do something more than that. Even when the formula is not satisfiable, we want to find an assignment. that would satisfy most, i.e., largest number of clauses in F. For example, if you look at a particular uh, instance, okay. So as we have seen, there's no way to satisfy all clauses here. On the other hand, if we make an assignment, we make assignment like this, okay, then we can satisfy three clauses. Okay, since there's no way to satisfy all four clauses, so this is the best assignment. Okay. Um, so the set problem is it's not a decision problem, i.e., that's not only asking you to give a yes or no answer, that also there needs a solution for that. Okay, so this is an optimization version of the set problem. In fact, the problem is actually also fundamental. Okay, that's a fundamental problem in computational optimization. Okay, and also this is a problem in terms of approximation algorithms. Okay, that also plays a role. Okay, that is similar to that of set in general algorithm design. So here is a survey. Okay, this is invited speech giving in artificial intelligence conference AAAI 16 in 2016. Okay, that shows how this Maxset problem is used in artificial intelligence. Therefore, let's get back to the problem. Number one, the problem is still NP hard. By that, we mean the problem is still too hard to be precisely solved efficiently. Okay. So because of that, there are many approaches to Maxset problem, including polynomial time approximation algorithms, or exact algorithms, or parameterized algorithms, and heuristic algorithms. Let's start with this approximation algorithms for Maxset. There's a very famous algorithm called Johnson's algorithm, okay, which is like a 45, almost 50 years ago. Okay, the algorithm is given like this. So basically, once you have a formula, we need to find assignment that satisfy the largest number of clauses. Okay. I'm not going to get into the detail of this algorithm. So the result is, this is proved by Johnson in his paper. Okay. Johnson proved that his algorithm has approximation ratio not larger than 2. Here, the approximation ratio is defined as the number of clauses that are satisfied by an optimal solution over the number of clauses that are satisfied by your algorithm. So Johnson's algorithm basically says that the maximum number of clauses that can be satisfied is no more than twice of the number of clauses that are satisfied by the solution produced by his algorithm. Therefore, in this case, the ratio, when you look at the approximation ratio, the closer to 1, the approximation ratio closer to 1 means better. Okay, of course, you cannot do more, less than 1. So when the approximation ratio equal to 1, that means your solution is an optimal solution. Therefore, we're looking for approximation algorithms whose approximation ratio is as close to 1 as possible. This is actually interesting. Okay, after like 25 years after Johnson published his result, we showed that actually Johnson's algorithm has a ratio 1.5. Okay, so that really means that if you use just a Johnson's algorithm, you can satisfy actually more than half. Okay, you can also do at the least just like how do you say, this is 66%, okay, if you compare to the largest number of satisfied clauses, okay. And we'll also show that this 1.5, this number cannot be further, improved. So for approximation algorithms for Maxset, so here's the list of results here. Johnson has this ratio 2 algorithm. Okay, then really after like 15 years, there's a survey. Okay, people ask, can we do better than 2 for Johnson for Maxset problem? But actually, as we just mentioned, okay, we have shown that in fact the Johnson's algorithm is better than 2. Okay, and in fact after that, there are progress. There are progresses for SAS algorithm. Yanakakis has an algorithm of ratio 4/3. So recall that remember this is a 1.333. Okay, and Gurman's and the Williams also have an algorithm of the same ratio, approximation ratio, was published in the same year. Actually, these two results, okay, are based on very different approaches. Okay, then after a few years, then Karlov and Zwick, they published an algorithm that has a ratio 8/7. Okay, so again, you can see you might expect a further improvement on that. However, okay, about the same time, Hasted proved that okay, for Maxset problem, you can have a polynomial algorithm, approximation algorithm, whose ratio is better than 8/7. So that really means that Karlov and Zwick's algorithm is the best possible. Has this result, okay, won the gold prize, okay, in 2011. The other approach for Maxset is called parameterized algorithms. This is a little bit different. Okay, again, you have a CNF formula, but now you're also giving a parameter k. Now you need to answer if there's assignment that can satisfy at the least k clauses. Okay, so k is given as as a parameter. Okay, and here is the first non-trivial parameterized algorithm for Maxset. Okay, this particular algorithm, the complexity is given, okay, by this recurrence relation, which gives a result that in terms of the parameter k, then the algorithm runs in 1.618 to the k. So recall that here the big O star means we ignore a polynomial factor. Okay. Well, so again, can you do better? Yes. There's also a line of improvements on this. So currently, well, we developed our algorithm about 15 years ago. Okay, so the complexity of this algorithm is 1.370 to the k, and which was improved, okay, after like 80 years. So the current best algorithm for Maxset is 1.358 to the k. In fact, this result won the best paper award at IPAC. That's a conference in parameterized computation. Okay. So now let's look into a bit more detail on parameterized algorithms. Okay. Recall that there are two hypotheses. Okay, one hypothesis is ETH that says for 3 set, okay, you can get a complexity C to the N, where C is arbitrarily close to 1. There's also a SETH that says that, well, for general set, Okay, you can't do, can't have an algorithm whose complexity is c to the n, where c is strictly smaller than 2. So this conjectures somehow show a popular opinion that really this branch in the search, seems unavoidable, okay, in solving set and Maxset problems. Therefore, in order to further improve those algorithms, we seem to have better, okay, branch and search strategies. Okay. Well, there is a very famous, okay, technique for set that is not based on branch and search. Okay, this is called a resolution. Okay, so let me give some definition here. So if you pick any variable, okay, if you pick any variable x, okay, and you look at two clauses, one is x or something else, the other is a negation of x or something else. Okay, once you have such two clauses, you can make a new clause with C or D. Okay, this C or D, this clause is called a reservant, okay, of this variable x. Therefore, if you pick any x, you find a pair of formulas. One contains x, the other contains negation of x. Then you can always make a reservant. Okay. And the resolution of a formula in terms of a particular variable x. Okay, this is a formula that you remove all those clauses, okay, that contain either x or negation of x. But then you add all reservants on x to this formula. Okay. Um, there's a famous, okay, result by Davis and Ponian. They said that once you have a Boolean CNF formula, okay, then you can also consider its resolution on any variable x. Then a formula is satisfiable if and only if its resolution, okay, is satisfiable. Therefore, in order to decide if a formula is satisfiable, you can instead, work on the resolution of this formula on any variable. Okay. So but that's good, right? Because the resolution eliminates a variable in the formula. So why don't you just repeatedly uh, use the resolution and to get rid of all these variables? Okay. But the problem here is that if you do resolution, okay, then you increase the formula size very quickly. Okay. Say suppose you have a formula that has n m clauses. Okay. If you do a resolution on a particular variable, then the size could be increased to m square. Okay, that's the number of clauses can be m square. Okay, so this is kind of bad. This, so when you start with m clauses, then you might have to go to m square clauses. Okay, so that you only eliminate one variable. So if you want to eliminate two variables, that your size might go, to m to the fourth, and so on. Okay, so then in that case, your formula size will increase very quickly. Okay, and that would definitely just hurt your complexity for solving it. Okay, well, but really for parameterized algorithms for Maxset, okay, there's not a problem here since we have something which is called a kernel. Okay, i.e., if you have a formula and have a k, you want to decide if there's an assignment that satisfies at least the k clauses. Okay, and then there's a result that shows that if the number of clauses, okay, is larger than k squared, you can always, directly give an answer for that. So that means we really for parameterized max set problem, we only have to, worry about, we only have to worry about it, the instances whose size is bounded by 2, k square. Okay. Therefore, this is a way you can do it, right? So basically, once you have a formula, you first can use resolution. Okay. The resolution will limit a variable. Okay. But, well, that might increase the size of the formula. So in that case, use kernelization. So remember, this is one that's going to keep the size, i.e. the number of clauses in the formula to be k squared. Okay, you repeatedly use this, then you limit all variables. So surely then you have a solution for that. But now the problem is really this: once you do resolution on a variable, okay, you actually, it's hard to control or to estimate, okay, the number of clauses in the optimal solution. Okay, so here's an example. So you can look at each of those formulas here. You start from the left. Okay, if you do a resolution, you would get the right. So for this one, in fact, the left has, you can satisfy 22, clauses, but on the right, you can satisfy at most 20 clauses. So the difference is like a 2. On the other hand, the second one, if you look at, okay, then the resolution and the original formula, if you look at the optimal solutions, they differ by only 1. And even you can look at even the third one, okay, and then in this case, the resolution and the original formula have the same number, you know, satisfied clauses in the optimal solution. So this means that if you do a resolution, you do not know how to control, okay, the optimal values here. Okay. So that's, again, we got stuck. Well, but let's look at the resolution again. Okay. So number one, we know, if you apply resolution, then you may get a much larger formula. Okay. That, and also, but now the optimal solution for the resolution. Okay. That depends not just on the solution. That also depends on the structure, i.e., on the clauses that you apply resolutions on. Okay. But if you look at the, this kind of simple, suppose you have for example, you have a variable, okay, that appears in very few clauses, like this example here. So x appears in only 2 clauses, and x bar, a negation of x, appears only in 1 clause. Then if you do the resolution on x, you would get a formula which actually quite simple. Okay, so that means the degree, when we say degree, that means really the clauses that x and x bar appear. Okay, so if the degrees are small, it seems it's quite simple, okay, to handle it. On the other hand, okay, if when the degree is large, okay, then we don't know how to do that, okay, because the structures can be too complicated. Okay. Well, on the other hand, okay, if you look at when the degree is large, in fact, the branch and the search process is actually more efficient. Okay, as as we indicated that in this. Okay, so this is what we may do. Okay, so in order to solve this parameterized version of Maxset, okay, we just pick a small, a variable of small degree. If that is a simple enough, then we can use resolution to solve it. Okay. Otherwise, okay, if the degree is large, then we may just branch on x. Okay, that's basically the idea. However, in order to do that, we have to be more careful. Okay, so whenever even the degree for the variables, even the degrees are small, it's not always easy to handle. Okay. And also we might have to use variations of the standard resolution here. Okay. So now first let's look at the case where the variables have small degrees. Okay, so degree 1, we can handle that directly. Degree 2, we can apply just resolution directly. Okay, and degree 3, actually there are some known results for this. Okay, so in that case, now we add two more, you know, resolution rules to this. Okay. So with all this kind of ways, when we solve that, okay, we can use the new techniques to solve um, the Maxset problem, okay, more efficiently. So, for example, okay, for particular this, if you restricted degree of the formula to be at most 3. So, by the way, degree of a variable is the number of clauses in which the variable or its negation appear. Okay, so once we say degree 3 formula, that means okay, for every variable there are at most 3 clauses that contain the variable or its negations. So it's a restricted version of Maxset problem. Then for that problem, we can solve that a parameterized algorithm. We have a 1.1, we have a 1.194 to the k algorithm. Okay, this is a very recent, and that algorithm actually improves the previous best algorithm, which has a complexity 1.2721 to the k. And I also use the same technique if you consider the algorithms in terms of the parameter n, i.e. the number of variables, then our algorithm has a 1.237 to the n complexity, which also improves the previous best bound, which is 1.26 to the n. Okay. Well, we can do a bit more than that, right? So we can also consider variables of degree 4. Okay. In that case, we also introduced two new resolution rules. Okay. And with these rules, okay, we can eliminate a certain clauses. Okay, those are the bottleneck for previous algorithms, and we get the following result. Therefore, now for general, for Maxset problem, we have an algorithm whose complexity is 1.325 to the k, which improves the best previous algorithm whose complexity is 1.358 to the k. Okay, and we can do further. Okay, and the further also leads us to improve the algorithm. Okay, in terms of the number of clauses. So this is basically the current status for parameterized algorithms. Okay, for Maxset. And in fact, in practice, there are a large family of heuristic algorithms for set and Maxset. So what is a heuristic algorithm? So heuristic algorithms solve the problem practically, but there's no theoretical guarantee on the correctness, or sometimes that doesn't, guarantee the efficiency of the algorithm. There have been many set or Maxset solvers. Okay, and this solvers actually solve most practical instances. Okay, in particular for set, very efficient. Okay, in fact, you use this practical solvers, you can solve, instances of like a million variables or clauses. The development of set solvers has been very impressive in the past more than 20 years research. Starting in 1990s, early 1990s, okay, our set solvers, i.e. algorithms for set or max set were able to deal with formulas of about, let's say, 100 variables and 200 clauses. By now, the modern set solvers can handle formulas of over 10 million variables and over 50 million clauses. Okay, so this actually says that the modern set solver, in most cases for practice, okay, in most cases it can deal with set or max set instances of very large size. The research in setting algorithms for set and max set have been very popular. Okay, there are two international conferences on the topics. One is called SET, which is the International Conference on Theory and Applications of Satisfiability Testing, which has been about 25 years since its first meeting. And there's also a relatively younger conference for Maxset, which is called a Conference on Evaluation of Maxset Solvers. Okay, but that has also run about 15 years. So those are the annual conferences. Researchers in set or Maxset algorithms meet in those conferences to exchange new ideas and to report new results. So let's go set. So this is the end of my presentation. Thanks for your interest. Bye bye.